Hi, today I'm gonna show you some experiments on robot nonlinear control uh, that I implement using micropython on Wokwi platform. Okay, first of all, the the link on the setup I gonna use is this tooling manipulator. Okay, we will do the simulation on software. Okay, and uh, first we want to model this robot that I have it on my book right here. I don't want to go into the detail of this, uh, but I will use this dynamic. Okay, so this is the equation of motion for this robot. We see that they have the inertia term. Okay, this inertia matrix, and they are coupled, right? And the middle part is the Coriolis matrix. Okay, that come from this symbol here. Okay, and the gravity term equal to torque. Alright, so this EOM that we will use to do the robot simulation. I have a lot of stuff here in this book, but we will continue on this. Okay, nonlinear multi-variable control. In this book, I implement three control schemes. Okay, the first one is PD control with gravity compensation, and I will use this robot dynamics. So in the book, let's talk about this diagram first. Okay, in this PD with gravity compensation, we have the more like a linear PD controller, but here we have the gravity term from the robot dynamics, and we compensate that. Okay, you see the gravity term. Okay, and I will add some model error to this block, so that in reality you cannot model the robot precisely, right? So there is some error of maybe 5% or 10%. Okay, and I implement using Scilab like this. Then I gonna show you. So here is the XCOS program for PD with gravity compensation. You can see that the 2D robot called planar robot here. Okay, is implemented as a super block like this. Alright, and I compute the initial term and also the Christopher symbol using this block. Okay, this block, and I put the equation in here, and the torque is applied on this input, and this super block gives us the q, the acceleration, the velocity and angle for each joint. Alright, so it's quite complicated setup, but it works quite okay. Okay, so first I have to set up the parameter that is used in the simulation. Okay, so this is like a link, length, mass, and center of gravity, and stuff like that. Alright, so here is the real model, and this one is the model that we get from there is some error, like I said, the error tolerant to 1. In this case, it is plus minus 5%. Okay, and here I use some cubic polynomial trajectory, so I want to see if it can track the trajectory. Okay, so we can run this and see that the output, the tracking output. Alright, so we see that the tracking is quite okay. There's some error because of the modeling error. Okay, from this you see that the control is also in the XCOS diagram. Okay, so this is the control. Okay, this is a robot dynamic. The control is also implemented as a block like this. But for real implementation, if you want to write some program to control this robot, you normally don't do this like you don't write it in block like this, but you want to write it as a micropython program, for example. That's why I developed this setup in Wokwi so that we can simulate our programming. Okay, and here I have the whole thing. I have the T control scheme implemented in here. Alright, this is quite a long program, but what I did is this. I have two methods of robot simulation. The first one is I implement a function that has that compute the robot dynamics like in this program. I call this sim2links. Okay, and you see that here is the dynamic. Okay, first I compute the initial matrix, each element of the initial matrix, right, and then the Coriolis matrix elements here, and then the gravity. All right, and then I first compute the acceleration for each joint. Okay, using the equation. So here is the equation for the robot, and I arrange terms such that I want to compute the acceleration for each of the joint, right? So it becomes this acceleration, and then I integrate acceleration. I get velocity, then I integrate velocity to get the joint angle. The indicator is written as a class. Alright, it's like a bilinear transform implementation, which is not difficult to do. Okay, so this simulation works quite well. Okay, the second method that I am using is to make it more challenging. I have my robot simulation in this custom chip. Okay, you see that I create a custom chip named Robo2Links here, and in this case I need to write some C code for that. Okay, as a separate file. This is what we set up to do the custom chip like this. Okay, and the robot dynamic is sitting in here in the timer routine. Alright, so it is execute each timer interrupt that we set up. In this case, I set it to 15 milliseconds. Okay, so this is a harder one than the previous method. That is everything is in the Python program. Like this. I have available to choose whether to use this simulation in the program or read data from the custom chip. Okay, the parameter is called plan sim. Okay, so I can choose that, and for this custom chip, the way to communicate with this custom chip is I use SPI. Okay, so I need to have some SPI code in this file as well, and I let's see here. Okay, here is the return part. For SPI communication, it's just like exchanging information from both parties, right? So the controller send the talk command to this chip, and the chip exchange the angle, velocity, and acceleration for each joint in return. Okay, so that is how it is implemented. So there are a lot of things going on in this chip.c, and I need to fix a few bugs. Okay, it takes some time to do that. Okay, Uh, so I want to show you first the PD with gravity compensation, right? So I have the code somewhere. Oh, by the way, this is the code for the LD ring. Okay, I have LD ring right here. Okay, NeoPixel to simulate the motor movement. Okay, you see in the moment that I have like a motor reference command position, and I have the two motor position that should track the reference command. Okay, so the code is right here, and I compute the link parameters using this function. I have a indicator class to change the acceleration to velocity and velocity to angles. Alright, so I want to find the first controller right here, PD gravity. Okay, PD with gravity compensation, and here is the code. Okay, so this is not very long. Okay, but it should conform to the X-cos diagram right here, right? So we have maybe it's better to use this diagram. Okay, so you see that the error from angle error. Okay, the error from the reference command and the two angle. Okay, cause the angle error and it fed to this p term. Okay, kp, and kd term use only the velocity from the robot. Okay, like this, and the gravity term use the joint angle. Okay, as a nonlinear function. All right, so that is the code. So I compute the gravity term for each of the joint, right? And then I compute the torque using that. Okay, conforming to that diagram shown earlier, and I compensate it using the gravity to this computation. So let's see if this works. So click run, and then I can use command to set up the controller that I want. Okay. Alright, so I think this is inward dynamic. If I can check. Okay, controller equal to 1 is inward dynamic. So I want to use the PD with gravity compensation. I set controller to 0. Okay, and then if I want to use the simulation in the program, okay, I can set psim equal to 1. All right, so that is use the function in this program. Okay, and let's see, this doesn't seem. So to prevent instability, I need to lower the gain a little bit, and now it is stable. I can adjust the set point. You see the green is the set point. Okay, the reference command for the motor, and the red is the actual motor position. Okay, maybe this gain is a little low. Okay, so it tend to track this one. Okay, if you want faster response, you can increase this KP and KD gain. Okay, but the simulation in this program is quite easy to implement. Okay, it works pretty much like the simulation in X-cos. Okay. But if I want to change uh, the simulation to this uh, shift, okay, this shift approach, I can set p sim equal to 0. Let's see if it goes unstable or not. Maybe it. Okay, it's quite difficult to switch the plan simulation on the fly because of the plan state. The difference in plan state made it become unstable, so I rerun it again. Right now I have a p sim equal 0, so I use the plan simulation in this chip. Okay, and let's see. If I change the okay, should tend to track this, right? Okay, so again, if you want to adjust the response, you need to play around with the KP and KD value. Okay, but at first it seemed to work quite okay. So I also implement some cubic spine polynomial. Okay, so that we can check if the tracking is okay or not. Let's see. I move it to 0 angle first. Okay, and now I set VR command to 0 so that I want to command I want to use the reference set point from my command, not from the variable resistor here. Okay, and then I can say track it seems a little slow here. Track equal I want to move this to some other position. Let's say I want to move the first joint to 90 degree and the second joint to 120 degree. I can use that command, and now the set point should move okay, so so at the end it should go to the desired position. Okay, so previously I thought it was 0 degree, maybe it's 360 degree. That's why it moved in that direction instead of counterclockwise. Anyway, I can see that tracking works okay for the PD with gravity compensation. So the second one I want to try is the inward dynamic. I can say controller equal to 1. Here, this is the inward dynamic. Alright. And let's say I want to move it to 0. Okay, this is R offset to 0, 0. Okay, so it should move to that. That is the 0 angle. Okay, and now I can use a VR command to check if it can track I can change the command reference command position using this variable resistor. Okay. So this inward dynamic simulation using this chip. Okay. Using the plan simulation on this custom chip. If I want to try the simulation in this program, okay, I can say psim equal to 1. I'm not sure that it got unstable or not, because when I switch the plan like this, this seems to work quite okay. Alright, so this is the plan simulation in the program. Okay, and I can say r equals 0, 0 to move it back to the 0 position. Oh, sorry, I need to set VR command to 0. Okay. Now I want to try tracking with the inward dynamic. Okay, and I say track. Let's say I want to use tracking to 150 to 70. Okay, it's quite a long move, and it do the cubic polynomial trajectory, and you can see that the inward dynamic track quite well. Okay, to the desired position. This is the case when we use the simulate plan in this program, but things doesn't work well for the tracking mode on the chip. Okay, here I want to show you. If I say psim equals 0, then I use simulation on this chip, and you can see that it goes unstable. So I need to restart the program, and now here is the inward dynamic with the simulate plan in the custom chip. You can see that when I move the set point using this variable resistor, it seems to work, right? But I cannot do the tracking mode. Okay, let's try that. I say VR command equals 0, and let's say I want to track to 50, 70. Okay, you will see that it doesn't work quite well. All right. Now you see the deviation of the real plan angle. Okay, it should track this. Alright, so you see the actual command position move here, but the real border angle is not what we expect, right? It doesn't work well compared to the simulation in this program. Alright, so what I want to say is the simulation here using the custom chip is more challenging, right? Because it has its own time base for the simulation, right? Just like two systems try to communicate with each other through messages, something like that. All right, so use the SPI to send, exchange the data. All right, it doesn't work well in the tracking mode. And here the control block diagram for the inverse dynamic. Okay, you can see that. In addition to compensate only the gravity, now we compensate the whole thing. Okay, we use the inertial matrix that is has some error. Okay, and we compensate. We use that, okay, in our controller as well. And also this term consists of the gravity and also the Coriolis matrix. All right, so we use all of them. And for here we use KP and KD. Now we have velocity error. All right, instead of in contrast to the PD with gravity, we only use the velocity from the real robot, right? We only use this term, but for inverse dynamic, we use both the command velocity and the real velocity from the plant, and then form the error, right? The command acceleration is so used because we create this using the cubic polynomial, right? Okay, even though it works well with the simulate on the plan simulation in the program, okay, because it uses the same time base for simulation. This is also true for adaptive control. Okay, if I change this to psim, go to 1, okay, and I change controller to 2. This is adaptive control, which is the most complicated of all. But you can see that if the simulation is done in the same program, it works okay. All right, so we are command go to 1. No. Okay, so I need to rerun the program to avoid instability. Now I have adaptive control and the plan simulate on the micropython program, and you can see that okay, even though it's a little oscillatory, but it eventually go to the set point. Okay, I have like a simple block here to implement adaptive controller. Okay, so all of these are the control. And we have like a adjustable learning parameter lambda and other sub, and here is the robot simulation. Anyway, I can show you that the simulation in the course work okay. Okay, see that I have 3 segment trajectory like this, and it can track the command angle quite well. Okay. This section of the book discuss adaptive control. Okay, you can say that we have like this we use linearity in the parameter to form the controller. Okay, this somewhat quite complicated. So let's see the diagram should look like this. All right, so we kind of have to form this y matrix, all right, and estimate the parameter theta here, okay, and then integrate. Okay, so here are all the adaptive controller. In case we don't know the true parameter of the plan, but we know the form, we know the form of the equation. So the parameter are lambda, the learning parameter, and here I have k theta and kv. Okay, these are all the parameters. Here is the y matrix. So let's go back to the program. Okay, so I write this adaptive control function that look like this. I compute the difference that is required, then I form the y matrix. Okay, each element of the y matrix here. So this is passivity based. Okay, adaptive control. Then I use the integrator inside to integrate this. Okay, so then the torque of the motor is computed in this. Okay, so as I show you here, the adaptive control work quite okay when I use the simulate plan in the program. Okay, and I can do tracking. Okay, I can track to some some target position. Okay, and you can see that we can do tracking. Okay, without instability. Okay, but I'm quite hopeless with when I use the simulation on the chip. Okay, it doesn't work at all. Let's see if I say psim. Okay, it goes unstable. I need to restart the program. Now I set the controller equal to true, which is the adaptive control, and you can see that it doesn't work well, even though I have stationary command set point. Like here you see the oscillation. It doesn't go stability is not okay. Okay, so you can see it goes on like this, so it doesn't work. So the conclusion in this experiment is I can do simulation that I use on the XCOS before. I can implement it on micropython program, and it worked quite okay when I simulate everything in the program here. Okay, but when I move the robot to the custom chip, okay, using Wokwi custom chip right here, okay, I cannot do complicated nonlinear control such as this adaptive control. Okay, I see that it has it tend to track the target position, but it kind of oscillatory, and this is not an acceptable performance. Okay. Anyway, this setup is quite interesting and it works for some degree. Okay, so if you want to try some other control, maybe you want to type reinforcement learning to train to do the this tooling robotic control. I think this should be a good setup, okay, to experiment with that. Okay, that's all I have so far. I want to play around with this more to see if I can improve the this setup.